Okay, let's go with topics. I'll call this topics from Fourier Series. And of course, that subject is far, far bigger than a single lecture, so I have to try to pick out a few highlights. I've tried to identify here some of the highlights. This Parseval fact that the energy in the function can be computed from the energy in the transform. The subject of the lecture then is Fourier theory. I usually write the subject up here. Fourier transforms between u and u hat. U of x, let's say, or u of t, and u hat of k or omega, whatever we call the transform variable. Okay, so this is a nice topic, and it really, this fact of energy inequality, energy equality, it comes about for other orthonormal bases. Convolution, although everybody would love to find some convolution rule that worked for beyond the Fourier basis. It's the Fourier basis that has this that multiplies so nicely, and of course the convolution rule is connected with multiplication of functions, and so I think it's just never going to happen that you're going to find a convolution rule for other bases that's as great as this one. And then I'm a little nervous here about the Poisson summation formula and aliasing. Maybe those qualify as topics, and convolution too for that matter, as topics that math majors are criminally deprived of in a lot of, well, convolution would show up in math courses, but many mathematical analysis courses focus on topic 4, the convergence of the Fourier series. So let me say convergence of the Fourier series. As I take more and more terms, does the Fourier series really approach the function it came from? That's led to a tremendous amount of deep mathematics. And you can ask a question of convergence at every point, or at almost every point. You can ask whether the energy in the difference is approaching 0. The difference, so I have a function f of x, and I'm comparing it with a part of its Fourier series. I'm looking at the difference. Does it go to 0? Does it go to 0 at every point x? Does it go to 0 at almost every point x? Does the energy in the function go to 0? So now the norm, the L2, this question is asking about what happens if I square it and integrate. That's what I mean by the norm, the L2, the energy. Does that go to 0? So do I converge, maybe not at every point, but in some mean square sense? And what does weak convergence mean? Here I am doing exactly what I said math courses do too much of. Number 4. It's the familiar thing. So in the back of my mind, of course, what I'm doing is doing it real fast and going to leave it. So I promise to leave it alone in a minute. But this idea of weak convergence, it's the idea of weak. We found a weak form last time that turned out to be totally central and important. The weak form in minimization. You remember when we minimized? We got a weak form of the equation, of the Euler-Lagrange equation. And what was the point of that weak form? It involved test functions. There was, for every function v, you integrated against v. So instead of squaring the thing itself, instead we'll just, now I'm doing weak. Instead I'll ask if I take the difference and multiply by some test function and integrate that, does that go to 0? It's going to 0, of course, as n goes to infinity, as n gets bigger, as I take more and more terms. Do you see that that's like not asking us much? For example, if I took the delta function, do I get pointwise convergence from its Fourier? Well, what is its Fourier series? I guess I'm caught up in this question, but I think that to understand these three ideas is not bad in a short time. So what's the Fourier series for a delta function? Really, a train of delta functions, because I'm doing the interval minus pi pi. So I think they're constants, right? Whatever constant it is, 1 over 2 pi or something like that. So does the Fourier series pointwise approach the delta function? Well, no. Of course, it can't. At x equals 0, this thing is, whatever it is, it's infinite. And so the distance to infinity doesn't get any smaller, even if you get larger and larger numbers, which of course you do. Does it converge in that norm sense if I square it and integrate? I don't think so, because delta squared will give me that infinity again. I think that in the norm sense, I can't do it. In fact, what does the Fourier series look like? Well, maybe I'll actually use the board here. So if I take the delta function and I compare it, its Fourier series then is the sum of are the coefficients 1 or 1 over 2 pi, I guess, 1 over 2 pi maybe? What is the formula for the Fourier coefficients? CK is 1 over 2 pi, the integral of my function, times e to the minus ikx dx, right? That's the key formula. That's the transform, or the inverse transform. I guess that's the transform. We start with a function f of x, and we transform it into numbers ck. And if that function is the delta function, the numbers, if that's delta, then the integral is always 1. That integral goes from 0 to 2 pi. So this integral will always be 1 for the delta function, and then I just get the 1 over 2 pi. So then that's the Fourier series for the delta function. And of course, I can add that up. Say from minus n to n, I could add that up. So it would come to something like 1 over 2 pi. I think it adds up to something like sine of n plus a half x over sine of a half x. It sounds like I knew that, but I wouldn't have known it if I hadn't looked before the lecture. So this is the partial sum. This is the sum over, this is the partial sum, and this is the thing that is trying to converge to the delta function. Well, in energy, it's not going to make it. Because if I graph this function, it's really high, of course, at 0. At 0, every term is 1, so I have a real peak there. But then it comes down, you know, it behaves like sine n plus a half x. It comes down there, it has a lobe there, it goes up, it does this, right? And symmetric, of course. Okay, so that's the partial sum. Well, that's not going to make it to the delta function, because these lobes, this side lobe, what happens to the side lobe as n increases? Yeah, so here I am really talking about convergence, but maybe it's okay because it's the delta function. You see, that wouldn't have happened in the course I took. What's going on here? You get these, the area, what happens as n increases? It sort of focuses, right? It gets narrower and taller, yeah. And the areas stay the same, right? Narrower and taller and the areas stay the same. And so my claim is that, yeah, it makes it in this weak sense. That if I integrate against some smooth function v of x, some smooth function, think how that smooth function v of x. Well, more and more as n goes to infinity, everything is happening near 0. And the right things are happening. I'm depending on cancellation, but the cancellation will be okay because my function v is practically a constant. That's the point, really, is that the reason this works is that for all practical purposes, v might as well be a constant, 1. And then that actually is correct. Of course, v isn't exactly a constant. It wanders away from 1 as it leaves 0. But the point is, as n increases, all the action is closer and closer to 0. This is really the integrated version of the Gibbs phenomenon. Maybe there's a useful remark that I kind of... I mean, the Gibbs phenomenon, of course, is when our function is a square wave. And then the phenomenon is that now that's a smoother function than the delta. Did I draw the delta function? I didn't really. Okay. If this is our function, it's one level smoother. The Fourier coefficients will decay like 1 over k, as we saw in the last lecture. We'll be a lot closer to the function, but we'll have this famous Gibbs event of this height. This height doesn't get smaller. The little wiggles get squeezed in, but the height doesn't get smaller. And the reason is that the height here, this height here, corresponds to this area here. Because we're sort of integrating this picture to get this picture, integrating a delta function to get a step function, and therefore the integral of an area will turn into a integral over an interval will give an area, which will show up here in the integral as a change in height. So there you go. I mean, this is like the most important, most troublesome phenomenon in numerical calculation, and we had a very interesting discussion during the break about it showed up again when we didn't have a periodic problem and hoped we did. Okay. I'm happy to pause a second here, and because I won't say more about convergence of Fourier series. Point-wise, if the function is very smooth, of course we can prove convergence. Oh, I'll tell you the big theorem that really excited Fourier analysts. A guy in Scandinavia proved a fantastic theorem. It was quite unexpected. That if the function had finite energy, then we know it converges in norm, in the energy sense. If a function with finite energy is in our Hilbert space, that's sort of the norm is the right way to look at the energy approaches the right thing, all good. But he proved for those functions that they also converge pointwise at almost every point. You can't, it's not true that they have to converge at every point. For example, here we've got a bad point, and who knows what's going on right at the jump. But this great theorem was that we got almost everywhere convergence, even if we only knew that the function had finite energy. That's pretty amazing. Okay. Is there any topic, any comment you would like me to add before I abandon number 4, this issue of convergence? I guess it's important to know the basic ideas, but those delicate examples that we mathematicians love, where it just about barely converges or barely fails, are absurd in practice. I mean, if it's that close, it's probably useless numerically, right? I mean, if it's only barely converging, then that's not going to be a satisfactory numerical method, so forget it. Okay, can I go to some of these other topics here? What about energy equality? Let's do that one. So, that theorem is this great fact that the integral of f of x squared dx can be computed. This is in the, what I've called over there, physical space. That this can be computed in Fourier space. And for the Fourier series, this is the guy in Fourier space, this is the guy in physical space. So let me put a circle around, a yellow circle around Fourier space. So what's the energy in Fourier space? It's discrete, so it's going to be a sum of ck squareds. And that's the correct formula, modulo remembering that maybe I need to insert a 2 pi or something factors depending on how I've normalized all these formulas. But the main point, you see, is this is the energy equals energy. Could I just ask you how to prove that? I mean, again, a mathematician would worry about the finiteness of these. Does this series converge? Does this integral make sense? But what the main point is that energy can be computed either in physical space or Fourier space. And why is that? How do I get from here to here? You write out f as a series. And all the, exactly. Keep the ones that survive and the ones that when we integrate, yeah. So we write out f of x as a sum of ck e to the ikx squared and do the integral. Yeah, it's just totally straightforward, and that's really my point here is that of course, now what does that mean? That's absolute value squared, so, and we have complex stuff, so that really would mean this thing times its complex conjugate. Can I write down its complex conjugate? C, let me use a different index, L, e to the, well, complex conjugate, e to the ILX, conjugate should be minus ILX, and now we're ready to integrate. Yeah, it's, and of course we're integrating over 0 to 2 pi. And what's the answer? You get 0. That's the whole point. The whole point is that if k and L are different, and our basis functions are orthogonal like these guys, that means their integral is 0. The integral of e to the ikx, e to the minus ILX is 0, except if k equals L. So when k equals L, the only terms we get are when k equal L. So all the other terms drop out. Well, then get an integral from 0 to 2 pi, we just have the sum of ck. Now L has to be the same as k, so it's ck bar, so it's ck squared. And this times this is just 1 when k is L. And I guess here we have a constant, so when we integrate it, we get the 2 pi. Yeah, so it totally... I just wanted to do that just to emphasize that everything came from, it was at this was the crucial moment where we used orthogonal, or orthonormal if we were really careful. Yeah. Yeah. That produced all the zeros that left these terms and exact equality. Okay, great. Great. So this didn't depend on Fourier. This depended on this orthogonal, so that we could have this true for Legendre polynomials, for Bessel functions, all those classical guys, all these orthogonal bases. And why are they orthogonal? Because they're eigenfunctions of symmetric things. Symmetric matrices, symmetric differential equations have orthogonal eigenfunctions, and they work. Let's see, what's the differential equation whose eigenfunctions are these guys? So I said, okay, I mentioned Legendre, which would produce Legendre polynomials, so he had a differential equation. Hermite had one. Who else? Bessel. Well, other people that I should remember here. But what's the equation that produces those eigenfunctions? Just u double prime, so it's embarrassingly easy, right? U double prime equal lambda u. Then u is e to the I kx, and lambda agrees with minus k squared, because two derivatives will bring ik down twice, and we'll get minus k squared. Good. So I guess nobody had the gall to, or hubris or whatever, to give his name to that equation. There we go. Yeah. Yes, at this guy, which was here. Yes.
So to do that, I guess after X, sort of well.
Yeah, that's right. Exactly. Yeah.
That integral being finite.
Right. That turns out to be exactly it. Exactly it. That's the whole idea of this L2 theory. First, of course, you start by first taking it really well behaved. It's a standard method. It was so well behaved that maybe it only has a finite number of terms. Well, then, of course, no questions. And then we want to let the number of terms get infinite and be sure that nothing goes wrong, and it doesn't go wrong as long as the overall final integral is finite. Yeah. So it's all going on in this Hilbert space. So this is like two representations of Hilbert space. We can think of functions that have finite energy in physical space, or we can think of coefficients that have finite energy in Fourier space. And so one is the Hilbert space L2, and this guy is the Hilbert space often called little L2. Sequence space, just as a discrete sequence of numbers. And Fourier and this Parseval equation is saying that the size of the function in the big capital L2 is the same as the size of the coefficient sequence in little L2. It's beautiful and extremely useful and almost totally elementary. Right. Okay. Let me go to the next guy on the list, convolution. Just sort of working down the list. Okay, so what's convolution about? Oh, by the way, we could have not only had energy I could have had two functions here. The integral of, let me use yellow, the integral of, I could easily extend that to the integral of f of x, g of x bar dx, two functions, not this, g doesn't have to be f, is what I'm saying, would equal, what would it equal over in transform space? If this function has Fourier coefficient ck, let's say, and this function has Fourier coefficients, let's say, dk, so I've got c's and d's now, what will happen? So I'll plug in sum of ck e to the ikx here, sum of dk e to the ikx here. I'll take complex conjugate, I'll integrate, and of course that integral moment is very crucial because a whole lot of zeros show up. And what's left? You'll get that same cancellation, so you'll have left a sum of the only terms that come up are when k and l are the same. And of course this guy is conjugated. And there'll be a 2 pi to fix it. Right. So just by totally the same. That says yes, if it's exactly the same cancellation that we saw here. Oh, I'm thinking f is written this way. Yeah, we're still totally in the Fourier world, so that this contributed no new idea beyond this one. It's just observation that totally the same method worked fine. Okay. So, but now we come to convolution. And what's the point of convolution? That we multiply functions. We multiply functions, multiply f of x, g of x. Now, and I'm not going to integrate it. When I integrate it, everything becomes easy. I want its Fourier series. Suppose f of x is the sum of ck e to the ikx, and g of x is the sum of dl, let me say, e to the I lx. Tell me, what are the Fourier coefficients of the product? So the product, so I want to know f of x, g of x. What are the Fourier coefficients? It has some Fourier coefficients. I don't know what to call them. HK maybe? Yeah, I'm like multiplying polynomials. Exactly. That's exactly what's happening here. I'm multiplying polynomials, so I just have to think, what does happen when I multiply polynomials? What happens? You get, right. And things are not dropping out here. Things are not going to zeros because we're not integrating anything. So what would, for example, what would h of 0 be? H0. What would be the constant term in the product? C0, D0 be in it, but not all of it. 1 and minus 1, 2 and minus 2. It's a sum over a big mess, right? It's a sum over all the C, J's, D minus J's, I guess. Is that right? And that's a typical entry in the convolution. So convolution is a messy thing to do. Here we did something that looked so pleasant, just multiplied two functions. But as you said, it's like multiplying two infinite polynomials. And so because they're infinite, because these sums are infinite, I have to expect that when I do the multiplication, each entry, each number, each coefficient involves an infinite number of products. Anyway, the shorthand is that this sequence of h's is comes from the sequence of C's and the sequence of D's by the operation that we christen convolution. Just gave a name to multiplying polynomials, multiplying functions, and just looking to see, hey, what do you have to do to the coefficients? So, but this is like, now, I just did the constant term. Did you see what happened? Now, what? Just to be sure, what's H1? What's the coefficient of e to the ix in the product? Let's just be sure we've got this guy nailed. What's the coefficient of e to the ix in the product? So I'm going to change now here to H1 and ask you for the coefficient. H1 now is the coefficient of e to the I1x, e to the ix, in the answer. So what? Add a 1 to j. Sounds good. Sounds good. Add a 1 to j. Cj plus 1, d minus j. Yeah, that's fine. So in general, of course, Hm is Cj plus m, d minus j, and this is a convolution. That's a for every m, yeah. And oh boy, you got to pick out the key point when you know how do you smell a convolution? The fact, what is it about these two indices that you notice? I could do it other ways. I could write it a bunch of different ways. Is that right? It's not. Yeah, that's right. I've got. But what? So what is it that they have to add to m? Right? They have to add to m. That's the point. That's the point. So if I just jump to a generalization instead of convolving a couple of sequences, what would it mean to convolve a couple of functions? I have a function f and a function g. So this is now going to be convolution of functions, where this was convolution of sequences. Okay, what should be the definition of convolving a function? Well, here I summed, right? So what do I do with the functions? I integrate. And it went from minus infinity to infinity, so let's do that, stay with that. Okay, and now what? These indices have to add up to, let's see, this answer is going to be some, what am I calling it? H, shall I use H? H, yeah, sure. Okay, all right, I'll put in the dx, because I know that belongs. So what's the convolution that produces h of x? I mean, what's the definition? This is just definition of convolution. I do want a different variable. Absolutely right. Absolutely. What do you like? dt? Yeah. Because 8x is coming out. Okay, now tell me what f at where and g at where. Well, as you just told me a minute ago, there isn't a unique answer to that, right? But so tell me an okay. What's the point of that? What's the point about those two numbers that they add to x? They add to x, right? Yeah, say x minus t and t. That'd be fine. Not the only possibility. You could take another because it would be just t and x minus t would be fine, certainly. Other possibilities, sure. Anyway, it's so you smell a convolution, or more than you know you've got a convolution when these add to x. And once you've sniffed out this convolution, what do you do? What good does it do to discover, hey, this was a convolution? take transforms. Thanks. That's exactly the right words. When you know you've got a convolution, take a transform and it'll become a multiplication. So if we transform these, f hat times g hat will equal h hat. Yeah. So in a way, you see what I've done here is like a little bit the opposite direction from what I did here. Here I multiplied functions and I convolved the transforms. Here I'm convolving the functions, I'm multiplying the transforms. But the whole point is really, you know, you could start in either space and switch to the other one. So the convolution rule goes both ways. Multiplication in one space is convolution in the other. That's the idea. Okay, and the importance in practice of this convolution rule is enormous. You know, the way I said about integration by parts, that it seemed like just a trick when you learn it in calculus, but in reality, it's a very, very fundamental idea. Similarly, here, it might seem just a trick, but it's got so many valuable applications that I'm okay. Okay. Now I'm working backwards to something that I wrote on the board before the lecture started, and I would like, it's Trefethen's master plan. And I figure when the author has a master plan, it deserves to get mentioned. So can I just say what's this master plan? Well, what's the connection between u of x and u hat of k? It's the Fourier transform. Okay, good. What's the connection between u of x and this sequence of numbers? This is what we were doing in the last lecture. I didn't use a v. I used a uj, but now probably safer to take v, to give it a new letter. So this is the grid sample. Grid sampling. Right? From the function to its samples. Okay. Now I have a function. I've got a sequence of samples, right? So what's the transform? What does it mean? What's v hat? Yep. So here I've got a sequence. Yeah. So I mean, morally speaking, I'm taking the Fourier transform, but it's somehow discrete, right? I have a discrete function. So what kind of a object is this? Yeah, I'm really just trying to identify what the heck these guys are. What yeah, so this is somehow the discrete time Fourier transform in EE language. Take a discrete thing and produce a what? No, that would be the DFT. That's where everything's finite. Here I've got, this is on the whole line, so I didn't say that. This was on the whole line, R for the whole line. This is on, well, there's a nice notation, Z for the integers. X is anywhere on the line. J is an integer here. Now, if I do the Fourier thing from a sequence, what does Fourier take me to? If I start with a sequence, it takes me to a periodic function, exactly. And of course, the transform or the inverse transform goes the other way. If I start with a periodic function, as I was doing here, I produced a sequence. So this was, I don't know what, should we call that FS, Fourier Series, or function to sequence? Or, hey, that's beautiful. Perfect. Okay, this is not maybe so well known, going from sequence to function, but of course it's just, well, when I say it's not well known, it's ridiculous. All you're doing here is doing this summation. There's the function. Start with a sequence V, put it in, add up the Fourier series, and you got the periodic function. Yeah. So this is fine. Okay. And now, now the question is, what's that? What's the connection between this and this? This is the brilliance of this diagram, of this master plan, is that each step crossways is just a Fourier transform. Here, let me write them in. Here it looks like I've got a function, so probably that's got to be a regular. No, that's a function to, oh, I better just, yeah, this is my interpolation function. Now, it's a true function, so I think that's a true Fourier transform. Yes, Pathan allows me to write Fourier transform on that. And, of course, he allows me to write, these are functions to functions. But now this is discrete, so this is the discrete guy. Okay, those are all easy. Horizontal is easy in this picture. It's vertical, but that's interesting. Okay, so we do the easy, the vertical ones we know how to do, and then maybe time will run out. Okay. So how did this connects to that first lecture totally. I mean, it's the same author here. So what was the connection between the discrete values of u? So we have a function u. We take its discrete values that I previously called uj, now vj. And what do we do at this point, at that stage? We interpolate by something. Band limited, polynomial, whatever we're doing, we interpolate. Maybe that yellow stands out well, so that step was sampling on the grid. This step is interpolation. Okay, what's that step? Well, everybody sees that step. Differentiation. Differentiation. And what's the final step here? Probably sampling, right? Isn't this what we did in the first lecture? We didn't know the function, but we imagined what we got with these samples that came from some unknown function. So we worked with the samples by interpolating to p of x, by taking the derivative p prime, and then sampling the derivative. Didn't we do that? I think. I did that without looking. Yes, that's what he said. Okay. And all I ask you to do is fill in the remaining dots. But you see how nice it is. Okay. Actually, everybody's going to be okay with that one. What did we do? What did we do at that stage? We multiplied by ik. We took p hat and we got ik p hat. And why did we do that? Because over here, that corresponds to taking the derivative. Right. So the most brilliant thing we can say here is multiply by ik. Right. Fine. Okay. And that's the familiar rule that if you differentiate the function, you multiply the Fourier series by ik. And let's see. Okay. Oh, well, this interpolation, no, but I should remember what interpolation we did. We're in the Fourier world here now. So how did we do that interpolation? We did the band limited one, right? I'm not going back to that polynomial method. That wasn't Fourier related. We did Shannon interpolation or band limited interpolation. And what did that do? Do you want to? Shall we have a guess of what this one is? We band limited it. We killed it outside the band, right? We low pass. We did an ideal low pass filter. What word? I've got the most. I never have space on this board, so I'll just put kill outside the band. Right? Yes. Right. Okay. Set it to 0. All right. And now I'm going to have a, well, I'll read this one out. Okay. Okay, so what do we do with this at that point? Huh. So I'm taking a function, I'm sampling it. Yeah. And this guy is still waiting for me. I'm watching the clock, but it's not going fast enough. All right, let's go for it. The step here, so the question is, how is this thing related to this one? Well, now let's first of all figure out what we're dealing with. Here we're dealing with a function that's defined for all k, right? So k is a real number here. And what's k in this case? Oh no, k is, sorry, no. Let me say it differently. K goes from minus infinity to infinity here. Right. All frequencies. Now what frequencies do we have here? We did the ones in our, where are we? No, we haven't done it yet. No, I'm not gonna get off so easily. Okay, let me write in the words that he has here, right? Okay, he wrote in these words, aliasing formula. Okay, now what does that mean? That's not a familiar, that's two familiar words, but put together, what are they? So I need a little space. And what they are is this Poisson summation formula. So that's what he refers to as the aliasing formula. And that was a new expression to me. So that's really, let's focus on that final issue, is what is this Poisson summation formula, also has an alias. Its alias is the aliasing formula. And what is it? So it's an identity. And I looked it up in the text, in the course text. And I found entry for Poisson summation formula. And actually I had used this formula, but I never feel I really know what it's doing. And now I really feel I don't know what it's doing because I didn't recognize it in Trefethen's form. So I'm going to write two forms of the Poisson summation formula. One form will be what's in the textbook. The other formula will be what's in Trefethen's book. And he says it's the same formula. And so this is like my hope that we figure out what's going on. Okay. So let me find that formula first as what I thought was Poisson's formula. It's an amazing formula. I have a function f, and I look at that at equally spaced points and add up the result. And I take its Fourier transform, and I look at that at equally spaced points, and the spacing isn't quite the same. There's a 2 pi in Fourier's world, that unfortunately. So these are spaced by 2 pi, these are spaced by 1. I could change, if I could change one spacing, I'd change the other spacing. So the product of spacings is 2 pi, of course. And there's probably, and then I add up these guys, and fantastically the things come out the same. Modulo some factor 2 pi always involved in the definition, which we could adjust the normalization. But isn't that amazing? So your functions, your original functions are on f of x is on x is on the whole line, and k is on the whole line. So we're starting with functions on the whole line. And then we're sampling and adding up their samples and their Fourier samples, and we're getting the same thing. Okay, so that's what I think, what the book describes and actually gives you an explanation of. And now let me give what he says is the aliasing formula. Now that'll be over here in this language of V's. He says that V hat of K, so I've got the transform side coming on the left here. Oh no, here's the sum from minus infinity to infinity. This is J of U hat of K plus 2, there's 2 pi has to appear. Oh, and since his sampling interval was, the sampling interval was H, so an H has to appear. See, I'm going to talk a little, but probably nobody's going to listen, right? Because you're naturally want to figure out what's the connection of those two formulas, and so do I. I suggest that we look at it a little bit, but if we don't get it completely straight, it's worth our time to think about it, to email. Let me put my email again, gs@math, about the right way to look at that. And now remember what's going on here. This V is the V's are the samples of the U. So the connection is that Vj is the U at JH. Sorry? Is the U the same as F? Well, okay. Probably. But I mean, those are two independent statements, right? I mean, you know, I come in this door and put this formula up. Trefethen comes in this door, puts up this formula with this connection between the V and the U, and he says, oh, that's just the same formula. Okay. So what's going on here? And anyway, this is then the link between. This is Trefethen's link between U hat and V hat. Right. Which is crossing? The first formula? Yeah, that's right. Yep. I'm willing to say yes to anything here. Yes. That's right. I mean, yeah. I just think that's kind of fun. In this guy, I'm pretty sure that's if you ask Poisson, that's his. Okay, I won't take that bet. Yeah. Yes. Right. Yes. Okay. Yes. Okay. Again, I believe that sort of thing is the key. Yeah. So I just think, well, first it's kind of fun and scary, but fun that here are things that are, we're talking about equations here. So we're not talking about, you know, complicated estimates for boundary value problems or something, but identities. And here we have a couple of remarkable ones, and they're also, not only that, they're disguises of each other. They're really the same somehow. And you see what it's saying is that where does the word aliasing enter here? It's saying that really that we get the same V from a whole lot of different U's. and we kind of know that, right? V is only determined by u at the sample points. So you could have other frequencies in it or not that V wouldn't know about. I guess maybe is that the right way to think about it? That if I add to something, if I add to u something that vanishes at all the sample points, like sine x over h or something, what will be the change in V? None. At x equal jh, the sign is 0. So somehow u has some... did that make sense? Yeah. Yeah. Yes. Right. Right. Yes. And that's why I get this thought. Right. Right. That's right. That's right. And now I'll be happy if you connect it to what I thought was Poisson's formula. I think it's... yeah. Yeah, you're sort of adding up things, kind of periodizes it. Is that a way to say it, or something? I don't know. Yeah. 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 I think if everybody's willing to copy down these two formulas, I'm game for anything next time. Yeah. Does that sound okay? Sorry? Oh, this is under Poisson summation formula in the book. If you look in the index, you'll find it. Okay. Can I close with a totally different comment? Just because I want to leave that one. I learned something this week which I should have known. I should have known to tell you about in Lecture 1. About inverses of tridiagonal matrices. And here's this wonderful fact. How can you recognize the inverse of a tridiagonal matrix? So, is it all right to come back to like ancient history, tridiagonal matrices? Okay, so it's make it symmetric. So symmetric, tridiagonal. What does the inverse look like? Well, we had certain examples, right? Our matrices, what did we call them? K and T. We computed their inverses. But now the comment is any symmetric tridiagonal matrix. Its inverse looks like, well, it's symmetric, of course. So if I tell you about above the diagonal, then I'm telling you about below. So a typical entry in row I, column J of the inverse. So this is now the inverse. Row I, column J. This is all these numbers have the form some alpha I beta j. Which is a very special form. So it's the same alpha for all along the row from here on, and the same beta all down the column to here. But of course that pattern stops when I go on the other side of the diagonal. It becomes alpha j beta I. And do you remember that that's what we discovered? You remember our specific concrete formulas for those inverses had there was a product of an I something times a j something. And now I discover that that's always the case, that every symmetric tridiagonal matrix has this form. So isn't that remarkable? And here's what's really satisfying about it. How many parameters are there in a symmetric tridiagonal matrix? N by n, of course. How many independent numbers tell us what this symmetric tridiagonal matrix is? 2n minus 1. Right, 2n, because we got n on the diagonal and n minus 1. So 2n minus 1 numbers. And what about over here? Same. Because I could normalize, since these are products, I could normalize alpha 1 to be 1, let's say, without, and then that would determine all the others, and there'd be 2n minus 1 of them, and it would agree the number of parameters. But of course, this is full matrix, and this is sparse. But the 2n minus 1 parameters are there in both, so you know you're sort of onto the right track. Yeah, so I thought I would just mention that. So this is all matrix. If I had a matrix like this, its inverse would be symmetric tridiagonal. I mean, it's a perfect match between this type of matrices and their inverses. And I hadn't even known about that. So there you go. That's kind of satisfying that we did examples, and then now the general case shows up. Yeah. All the rest, yes. We realize that we've only got this many numbers somehow to find. Where we thought we had to find n squared numbers, now we realize that it's really only O of n numbers that are in a book, or in a paper, I should say. I can give you the reference because the guy sent it to me. But so he's summarizing, and so it's not ancient history. So he gave credit to somebody named Asplund 40 years ago or so. But the paper that I read it in, and gives a nice proof and everything, is, I can give you the reference. Morant is the author, and it's in, I'm happy to say that it's in Siam Review in 1992. Yeah. So you might enjoy. If you like those tridiagonal matrices, here's a fact that very important fact that we missed at the time. Okay, we're past 4:30. Thanks, and please help me out with the alias of the Poisson summation formula. Thanks.